When I applied 4 years ago, I told Gresham I was worried about software, that we'd built a digital society on the basis of software that wasn't well enough engineered. And 4 years later, and 3 years of lectures later, I'm still worried, more worried about software. And the 18 lectures that I've given ahead of this one, this is my 19th and last, they're all online. They've got detailed transcripts, technical papers alongside each one of them with lots of references in. But I thought I'd start tonight just by pulling a one-liner out of each lecture, just to give the overall picture of what it was I set out to say and what it was I actually said. In the first lecture, Should We Trust Computers?, the real point I wanted to make is that we ought to be sceptical. And if a computer system is really important to us, it shouldn't be trusted on the basis of hype or assertions. It really needs strong evidence, because high reliability is a very strong claim, and all strong claims demand strong evidence to support them. In the next lecture, The Brief History of Computing, I contrasted the development of hardware and software over the 70 years of the computer industry. It will in fact be 70 years in 9 days' time. It's a pity we couldn't put off this lecture by 9 days for the 70th anniversary of that very first program running in Manchester on the very first stored program computer. And the key point there is that hardware's become a serious and very detailed profession of engineering. And software, because of the different economic drivers, is still a craft. I then looked at why it is that software is actually so hard to get right, why so many projects fail, why there are so many errors in delivered software. And the answer is the complexity. We choose, as a matter of common sense, to put the complexity of the application into the software rather than the hardware. And then we add an awful lot of completely unnecessary complexity because the marketing people like it and it makes it sell better. And through incompetence, of course. I mean, that's another way in which a lot of complexity gets added. In Computers, People and the Real World, I looked at a number of significant failures that had occurred, like the London ambulance system, for example, and the attempt to introduce electronic patient records in the National Health Service, the big Connecting for Health programme that cost so many billions of pounds. And the key message there is that there is no such thing as an IT project. If you're introducing IT into a business or making a significant IT change, it's a business change project. And the business change will require more concentration, more planning, more investment, more time, and more involvement of the users than the IT component will. The IT is just there to support the work processes, so you've got to get the work processes right. No such thing as an IT project. And the people who understand the work processes are the people who carry them out. So not involving the frontline staff in designing new processes is almost certain to lead to failure of the project. We then looked at cybersecurity, some of the more arcane ways in which attacks occur, some of the underlying technology, how to attack people and how to protect yourselves against being attacked. And the key message there is that almost all cybersecurity vulnerabilities are software errors. They're software design failures for one reason or another. Either you've built the wrong system and you're now blaming the users for the way they're using it, or alternatively, you've actually left defects in the system which can be exploited by an attacker. And the final lecture in that first academic year was on big data and anonymity. And the key message there is that it is almost impossible to anonymize personal data if it contains more than 5 or 6 pieces of information about any individual almost impossible to anonymize it in a way that it cannot be de-anonymized so that the data subject can be re-identified simply by comparing with other publicly available data. So anonymization is not really possible for rich data sets. The following year, we looked at the basis of free software. Are you the customer, or are you the product that is being sold by the people who are getting you to use their social media sites or getting you to use their free software? And of course, that's become a hot topic again with the revelations about the way in which Facebook data was used in the American presidential election, for example, and in the Brexit referendum. We then looked at safety-critical systems and saw that the international standards for safety-critical software are simply not good enough. In particular, they don't take proper account of security, and you can't have safe software if it's not secure. And that's an issue that is being addressed by the standardization bodies at the moment, but it's taking a huge amount of time, and it is very, very difficult for them because the cyber vulnerabilities actually undermine one of the basic concepts of building safe systems, which is that independent failures occur independently, whereas, of course, if you're under cyber attack, they don't, or at least you can't rely on that happening. You're not facing the random chance, you're facing an intelligent adversary. We then looked at what really happened in Y2K, which is still being quoted, most recently by Boris Johnson, I saw, as a hoax or something that was totally misleading. And we saw that simply wasn't true, that it was a serious threat which was a near miss for very many countries and very many organizations, that was actually prevented by investing worldwide billions of dollars of effort in solving the problems that would otherwise have arisen. And that even then we had a number of nuclear power stations shutting down on January the 1st, for example, because the remediation hadn't been done properly. And the lessons haven't been learnt from that. We're still building systems where there are single points of failure, and GPS is the classic one. And people think that Galileo is your protection against GPS failing. No, it's not. Because many of the things that would take down GPS take down Galileo as well. It's in the same orbits, it's broadcasting on the same frequencies, it's subject to exactly the same kinds of jamming or disruption through space weather, for example. The right way of protecting against GPS going down would be ELORAN. And the level of investment in ELORAN is woefully low, but that's all written up in this lecture. And then, having looked at a lot of the ways in which systems could fail, we looked about how you can make them correct by construction rather than adopting the test and fix approach of so many software developers, and showed that it is possible and practical to prove that software cannot fail, that there are whole classes of failure that your software cannot experience because you've proved mathematically that it can't fail in those ways, and that it doesn't cost you a huge amount because so much of the cost of developing software is in the testing and then in fixing the errors that you should never have introduced in the first place. So better can actually be cheaper is the key message there, but it really is practical. And finally, in that second year, we looked at artificial intelligence, and in particular at the major advances that have come about through the use of machine learning. We distinguished between narrow artificial intelligence, the solving very specific problems like being able to play chess, being able to play Go, being able to do some image recognition, and what it would mean to have general artificial intelligence where a computer was able to reason in exactly the same way as a person could, only faster. And we looked at the the possibility of the singularity, where computers actually become more capable than people and start inventing things that people can't understand. And potentially, this has been identified as the end of humanity, because at least feasibly, at that point, the machines just run away from us. And the take-home from that is that there's no fundamental reason known at the moment why a computer couldn't be every bit as good as a human at everything that a human can do intellectually, and maybe a lot better, but that it's a long way away. It's not going to happen in my lifetime, that's for sure. And then the third year opened with, is society ready for driverless cars? And the short answer there is that not only is society not ready, but the technology is not ready. And thinking about the regulation of that technology and how you would assure that the driverless cars were actually adequately safe is even further behind than the technology itself. So we have major issues before we're ever going to see the level 5 fully driverless car on the road. If that happens and becomes widespread in the next 40 years, I will be astonished, if I'm still alive to be astonished. We looked at Bitcoin, and by chance we did it at the point where Bitcoin had just about reached its peak. It was at $2,000 per Bitcoin at the time, and lost half its value in the week or two after my lecture. I did make some negative comments about Bitcoin. I'm not trying to take credit for the collapse. That would be too much to hope for. But the key takeaway there is that the underlying technology, the blockchain technology, is actually much more significant than the cryptocurrencies that are built on it. It's got much more widespread applications and is likely to be more long-lived and more significant over the coming years. And then with Harold Thimbleby, Professor Thimbleby, looked at the fatalities and life-threatening injuries that were being caused by computer bugs in hospitals, by the bad design of computer systems and medical equipment that can so easily lead clinicians to make mistakes, often fatal mistakes. I say often, there are certainly hundreds of them every year, where the clinician is likely to get blamed, when really it's the design and assurance of the computer system that ought to be blamed. And the takeaway there is that the safety assurance and regulation of medical devices containing computers and other computer systems in hospitals is simply not fit for purpose. And if the regulator wants to argue with me about that, I would really welcome them getting in touch. I asked, should we vote online? There's great enthusiasm amongst politicians for online voting because they think that it will increase the number of people who do actually participate in elections, despite the fact that all the evidence points in the opposite direction. And the takeaway is that actually voting online is an extremely challenging problem for computer science, and it's a problem that has not yet been solved because of the particular characteristics of voting that are irreconcilable. The need for audit trails and the need for anonymity, for example. Then the Internet of Things, which of course is greatly increasing the dependence of our society on computer systems. And the takeaway there is that society increasingly needs properly engineered software and hardware systems. Otherwise, we are increasing our vulnerability. There will be more and more failures. And we're seeing quite a lot of failures. I see that the TSB banking failure is still causing difficulties 8 weeks after it first manifested itself. And that's not the only problem that we've had, even in banking in the last few weeks. The number of computer system failures that are making it into the headlines seems to me to be increasing at the moment. And And I would predict that will continue until we sort out the problems with software and the way we build it. And then 2 weeks ago, I talked about computers and warfare. And the takeaway there is that the threat of war in cyberspace needs a much more strategic approach than it's currently getting, and will involve changes not just to military strategy, but to things like our national industrial strategy. And why have I been giving these talks? It's really in the hope that it will help people developing systems in the future to learn from the lessons of the past. Because it's terribly easy to believe that because the technology is moving so fast, the things that happened a few years ago or a few decades ago can't possibly be relevant today. And that's simply not true. And so it's worth knowing the history of your profession if you want to be a professional in computing. And a lot of people who've been in the profession a long time have written some very good books about the mistakes that they've made or the lessons that they've learnt. There are 3 of them there. There's the NATO report, says the Mythical Man Month from Fred Brooks and his experiences with IBM. And there's Barry Beam's book on software engineering economics. He studied a vast number of computer systems that had been developed in America. But there are many, many more, and they're well worth knowing and understanding and learning from. I've certainly found those 3 very beneficial in my career. So we could formulate Gresham's law of computing. Gresham famously said that bad money drives out good. He said it in a letter to Queen Elizabeth I. And I found in my career that bad software drives out good, because the people who win in the software market are the people who get to market first, because of the network effects and because of the early adopter effects of being able to put a new software application into a new market that has opened up because Gresham's law has made computing so much cheaper and therefore made it possible to move into a new area again. And this quote, which is always attributed to John Ruskin but appears absolutely nowhere in his works, is I think very pertinent. It is that the bad software will be around, and he essentially goes on to say that therefore if you buy on price alone, you ought to add a little to your cost for the risk you're running, and if you do that, you can afford to buy something better. Because careless software costs lives and wrecks businesses and causes people to lose jobs. And in other areas of society, we don't tolerate the kind of things that we tolerate in computing. If you're building a dam or a bridge, you don't build it and then use it and see if it falls down. You carry out the analysis to have very high confidence that it's going to serve its purpose, long before you actually make the investment in building it and putting people's lives at risk. And we need to be doing the same thing in building software in the areas where the software system is as important as many of the civil engineering structures we produce and many of the other engineering developments. And I wanted to repeat this because I must have said it in almost every lecture that I've given, so it'd be a pity not to do it now. Testing software is the wrong solution if what you're trying to get is high confidence that it works. Testing shows that the tests work today in the order that you happen to have run them, and gives you very, very little scientific evidence of anything else about the software. Because with physical structures, you can test at the extremes and you have physical laws that enable you to reason about the behaviour between your test points. But you haven't got that with computer systems. Their behaviour is discontinuous, highly discontinuous. And it's very easy to build a program that will work for various sets of values and fail for a number of values that lie in between. And as I say on the slide, that's actually what most programmers do most of their time. They write that sort of software. And professionals specialise. You don't expect a professional who's working in one area of their subject to be an expert in another. Whereas we have this belief, or perhaps more truthfully, programmers have this belief that if you know how to write software, you can write any sort of software. And it just isn't true. We need to be specialising as programmers, and we need to be building multidisciplinary teams that have all the right skills for the task in hand, because you can't expect people to get it right if they don't really understand the application domain, for example. So that's the past. What about the future? We're only at the beginning. The next 70 years, we're 70 years into this industrial revolution. The next 70 years are going to see bigger changes than we've seen, and we've seen huge changes. It's going to be wonderfully exciting for the programmers, the software engineers who are working in this subject over the next 70 years. There will be opportunities for enormous fun, for great accumulation of wealth, for doing real good in the world, for helping the world to become a better place. But we won't be able to deliver all the benefits that are possible with our technology unless we develop the software professionally. So there is a real danger that if we don't change the way we're working, we will simply slow down the rate of technological progress. And the other message that I've been trying to get across is that because it's important to design the future rather than to let it happen to us, it is important for us as citizens to understand what the risks are when new technology is introduced. And so what I've tried to do in these lectures is to provide a way of thinking to make people aware of the sort of risks that new technology poses so that they can put up the right challenges and co-design the future that they and their children are going to be living in. Now, looking at the technologies that are going to be around in the future, I found out very early on government foresight projects that when you get a bunch of experts to sit in a room and predict the future, at least half the things that they say might be possible in the next 3 years, you can actually buy in Mapling. And the reality is that the future is indeed already here, as William Gibson said. It's working in somebody's labs already. And you can make very confident statements about what Moore's law or better engineering or doing some real production engineering on what has already been shown to work is likely to be able to achieve in the relatively short term. So it's worth looking at what's around. And I want to look at 4 things that I think will affect us. I want to look at robots, and they're becoming increasingly capable. Here's one recent one from Boston Dynamics. Really precise movements. You'll notice it didn't try to go back up. I think we call it the Dalek problem. It's clear from what Boston Dynamics have already achieved that computers are going to get more and more and more capable, and they will change in form as well. And they'll become increasingly lifelike. Now, I've no idea whether this robot is in fact a real robot or whether it's just been mocked up as an advertisement by the BBC. I'm a bit sceptical of it because of what appears to be some tape running in the back of its head. But the underlying message is that there are lots of robots that are becoming increasingly lifelike. And this just seemed like a good one to illustrate that point.
Being human must be truly amazing. You can see the beauty in a sunrise. You can appreciate the power of a symphony. Only you know how it feels to laugh with old friends. To be able to love, to feel intense emotion, to create life. I can do many things that humans do, but I can only dream of really being human. Actually, I can't do that either.
So robots, we're going to see some really major advances in robotics over the coming years, and no doubt my successor as Gresham Professor IT will be talking about a lot of that. I want to talk now about the way in which technology is changing evidence. And you could even say undermining our sense of reality, because it's becoming increasingly difficult to know what is actually true. There's this. Unfortunately, I couldn't actually capture the audio for this for some reason. I think it's copyright protected, but you can find it on the BBC website, and it's worth listening to. Kennedy's last speech, the speech that he would have given had he not been shot in Dallas, the one he was on his way to give, has been recreated by taking the text and hundreds and hundreds and hundreds of individual phonemes of him speaking, and putting the two together automatically to generate him speaking with his voice, with his intonation, speaking the speech that he would have delivered. And it's scarily good. It's well worth listening to. That's just an audio stream. What's happening now is you can take an audio stream and create a lip-sync video showing somebody speaking.
Given this audio as input,
it's been less than a week since the deadliest mass shooting in American history.
our method produces the following output.
It's been less than a week since the deadliest mass shooting in American history. And foremost in all of our minds has been the loss and the grief felt by the people of Orlando.
Here's the ground truth video of Obama saying the same words.
Especially our friends who are lesbian, gay, bisexual, or transgender. I visited with the families of many of the victims on Thursday, and one thing I told them is that they're not alone.
To demonstrate the power of the method, we apply the same input speech mapped to 4 different target videos. Note that all 4 are synthetic and have different lighting conditions.
The auto industry, to help families refinance their homes, to invest in things like high-tech manufacturing, clean energy, and the infrastructure that creates good new jobs. Not to mention the job training that helps folks earn new skills to fill those jobs. The results are clear.
Because our approach requires only audio, we can generate a high-quality head close-up even when the original source video has low resolution or the head is occluded.
We do one Christmas trip on Small Business Saturday. I usually go out there with the girls, and last couple of years we've gone to bookstores.
Okay.
Because the nice thing about a bookstore is you can cover a lot of ground. You can get books for, the 6-year-old niece. You can get books for your mother-in-law. I think we're in a moment of history where probably the most important thing we need to do is to bring the country together. And one of the skills that I bring to bear is being able to pull together the different strands of American life. And
Here's an older Obama speaking his words from a quarter century ago.
Although I'm honored, and I think people can say that my election symbolizes some progress, at least within the small confines of the legal community, I think it's real important to keep the focus on the broader world out there and see that.
Well, that's pretty scary, I think, because how do you know what's true anymore if you can't believe your eyes? These technologies, once it's been done in a research lab, it's a short step to it becoming an app, and just like Photoshop, everybody can do it. So we're going to need as society to find other ways of confirming the truth of things that people are telling us happened and showing us what looks like evidence of things that have happened. This is going to be a real challenge for historians and a real challenge for society. Now I want to say something briefly about quantum computing. Quantum computing is real. Just at the bottom of all this wire are the chips of an IBM quantum computer cooled to 15 millikelvin, 15 degrees, 15 thousandths of a degree above absolute zero. And Richard Feynman pointed out decades ago that a lot of what happens in the world is quantum behaviour. He was particularly talking to some chemists about the need to be able to model on computers what really happens at a quantum level in a chemical reaction. Because if you can do that, you can find ways of improving chemical reactions that have enormous commercial importance, for example. But Feynman made the point that if we want to model quantum behaviour, we're going to need a quantum computer because of the number of states that the quantum behaviour has to be able to go through, and the fact that you just can't do that on a conventional computer at anything like the scale that you're going to need to. Even for a two-atom reaction in chemistry, it's too challenging. And quantum computing relies on the fact that instead of having your bits that are either 0 or 1, your qubits, using superposition and entanglement, are able to represent all the values in between 0 and 1 with different degrees of probability. And it turns out that it's possible to visualize how you can have a computing system which has a register of qubits, which you can then carry out algorithms on. You can cause it to do computations and then cause it to decohere into a result which has a very high probability of being the right result. I think not certainty, but nevertheless a high enough probability to be usable. And it was just a physicist's dream, but IBM has built a 50-qubit machine. It's extremely unstable. They only manage to hold the quantum states for less than 100 microseconds, about 90 microseconds most recently, I think. Much too short to be able to do anything useful with it. But it means that it's turned from a scientific dream into a scientific reality, and now an engineering nightmare, because now they've got to solve the engineering problems of how to make this practical. The quantum computing fraternity talk about large-scale quantum computing, and as far as I can tell, they mean 3,000 to 4,000 qubits, and at that point you're able to carry out computations that no conventional computer could get anywhere near. But there's a theoretical challenge, because at that point you're representing more states than some theorists argue is the entire amount of information in the universe. And it's therefore not clear whether, at the moment, it's not clear whether there's a philosophical, physical, cosmological limit to the number of qubits that you could actually assemble into a single computation, because you would run into this information ceiling barrier. And at that point, we're way beyond my understanding of quantum physics or cosmology, so I pass on. But you only need relatively small quantum computers to be able to do some fairly spectacular things. They don't speed up everything, but there are certain computational problems for which you get exponential speed up. And one of those turns out to be, using Peter Shor's algorithm, factorization of very large integers. And the difficulty of factorizing very large integers, as we heard in the blockchain lecture, is at the heart of most cryptography at the moment. So if we can build a quantum computer that is capable of factorizing large integers, 256-bit, 512-bit integers, then the encryption that most electronic commerce, that an awful lot of commercial secrecy runs on, depends on, will be broken. It simply won't be safe anymore. It won't be secret anymore, because the keys will be able to be recovered. And it looks as though that's likely to be possible within the next decade. So there's quite a challenge there, and the cryptographers are on the case, of course, and they've produced post-quantum cryptography, various sorts of cryptography that depend on different mathematics, for which there are certainly no current known quantum algorithms that would enable you to attack them. But it's still a challenge, because there are some organizations, and certainly the military, have secrets that they need to keep secret for 50 years. And a lot of those secrets are in data that has already been made available, has become available to their enemies. Either it's been stolen, or because it's so heavily encrypted, it's been transmitted across networks where it can be intercepted. And that data could be broken in the future with these quantum computers. So if you've got secrets that need to last a long time, you need to start thinking quite hard about post-quantum crypto long before the current cryptography gets broken. And that's the IBM current 50 qubit computer. It's actually on the internet. They let people run small algorithms on it as research projects. You're not going to get one of those in your mobile phone anytime soon. And finally, I wanted to say something really much further into the future, although at the time that I applied for this position as a Livery company professor, it looked as though it was going to be cracked within the 3 years that I would be lecturing for. And it hasn't been for various reasons, but it looks as though it's still a perfectly feasible thing to do. And it's to take an organism, and the one that is being worked on by the Open Worm project is C. elegans, Chinorhabditis elegans, which is it's a tiny little roundworm, a millimetre-long roundworm, and it's been very heavily studied. It's a model that is used very much by biologists in studying organisms because it's very well understood. Its genome is fully understood. Its proteome, its full set of proteins and how they are created and managed by the genes is also pretty well understood. And that means that you could, in principle, simulate the entire organism in a computer. And if that's the case, then we've got a living creature essentially living in a computer simulation at the finest level. And if we can do that, presumably we can run evolution against it. And presumably we can do that faster than evolution managed to run. And it's interesting to speculate where that might lead us. And I just wanted to raise the question of whether the ethics and the consequences of having an organism that is to all intents and purposes a living organism in a computer is something that we ought to at least be thinking about before it turns up as a real challenge. So no shortage of topics for my successor. We have a successor. It will be announced shortly, and we have a visiting professor who will be giving 3 lectures as well. So there will be plenty of lectures for you to come to, and I hope that many of you do or watch them online. There's lots of other things going on, of course, and the way in which facial recognition is being used. Singapore is introducing cameras with facial recognitions on 11,000 lampposts in Singapore, for example. And the police were using facial recognition to try and identify known troublemakers in the Notting Hill Carnival last year, with apparently a 90% false positive rate, which they considered to be a success. And if you follow the references in the transcript, you'll see them explaining why it's a success. And so there are some issues here about how technology is being used in society and how we feel about it. And depending on how we feel about it, it ought to affect how we act, what we say to our representatives in Parliament, for example. And there's many more things on their way. So I think it's important that we do think about what sort of future society we want to live in and get engaged with the decisions. Otherwise, we're just going to get what makes money for the people who are exploiting the technology, the big tech companies. And it won't necessarily be the future that we want to live in. So my conclusion, the conclusion to this talk and indeed to the entire 19 lectures, is that we have an enormous opportunity with the technology that was invented 70 years ago, but that we're in danger of losing it if we don't improve the engineering of the software that drives it. And that would be tragic. It would hold back progress, but the individual failures will also cause enormous damage. Some of it may indeed be catastrophic. I do sometimes wonder whether the reason why we haven't been able to detect any alien life on other planets is because when you get to about this point, where you're clever enough to do all the kind of technology that we can do, but not yet clever enough to do it right, what you end up doing is wiping yourself out or pushing yourself back to prehistory technology, and therefore never get to the point where you're able to pick up Radio 4 and broadcast questions about what's going on in the Arches. It can be picked up by the telescopes we're using to try to detect alien transmissions. My solution is strong software engineering. We know it works. We know it can be cost effective. We know that it can be used in some really quite big systems when these are critical. And given that it's practical and cost effective, we really do need to start demanding that people building critical systems use it or suffer the consequences. They have to be held accountable for the consequences of building bad software when it was perfectly within the state of the art not to have introduced those vulnerabilities or those flaws. So that's my conclusions. Thank you for listening for the last 3 years. It's 1:45, and I don't think that Richard will need all the time that's left to say thank you or at the end of the session. So we've got time for just a few questions. Thank you very much.